Hello, everyone. It's my great honor to be here to participate in this conference. My name is Han Yu, and I come from Zhengzhou University in China. Uh, Today, presenting my report about the solid-state Norbornadiene photothermal films for efficient solar energy storage. As we know, the demand for green energy is increasing. Compared to 2020, by 2050, the world's energy consumption is expected to grow by about 43%. Mm, As global energy demand rises and environmental concerns instead, solar energy being clean and renewable has emerged as a vital solution to address the energy crisis and climate change. Solar energy utilize primary involves photothermal. We call it the PT or PV technologies. PT systems capture the solar energy as heat, where PV systems utilize the solar with into the electricity via PV cells. We can see the molecule solar thermal energy storage system we call the MOST has obvious advantages. MOST systems store solar energy through light induced molecular isomerization, capture energy within chemical bonds on enriching the parent molecule become into a high energy system, which can release storage energy in the form of heat. We can say it is NDD has been converted QC, and it can store the energy. It's about his operating principle. Uh, a conventional thermal storage method only is such as sensible and letting the large storage is relying on physical force translation for energy storage and release. However, they are through thermodynamics processes indicate that they are not become they are release the energy with the temperature drop. Yeah, leading to significant energy loss and limiting their effective energy utilized due to the iteration generation. We can see this figure. The figure E is about the comparison with the traditional energy storage and the MOSD system. We can see with they are different is about the MOST can release the energy with the temperature up, but another is a drop. So we can collect the more energy for we use. The figure B is about the energy NDD2QC conversion process. Our figure C is about a schematic diagram of energy integration device. It's our finally objective. Is our this PowerPoint is about the object of research. Figure 8 is about the four NDD materials we research. We can see is only is different. These are all uh, organic materials. There are different ways about uh, the important group with we can say is all NDD converted to QC. Uh, the, the figure B is about the infrared speaker term of NDD4 in illustration changes in chemical bond before and after the photo is photo issue materialization education. And the fiction is about the SEM and EDS analysis. This is our experimental process. Uh, the figure A is our how to make this materials. It's and figure B, C, and B, C, D, and E is aware how to calculate of these materials. We can see it's different this about this is about the parameter of molecular films. So when we find this materials, we are thinking on how to improve it because it's a liquid system. Uh, as we know, liquid system is easy to leakable and is unstable. So we have found a technology to optimize MDD memory. We use the PS to optimize the NDD memory. The figure 8 is about our optical microscope energy of NBD4 films with four different PS ratios. The figure B is about the photographs of NBD4 films prepared with four PS ratios. We can see it has converted from the liquid into solid. It can improve its tensile situation and stress. It's we can make it integration of systems to complete this energy. The figure D is about the anti-error analysis of MIDI for film. So we for research his system. This system are the concept of NDT materials. We have used the quantity chemical simulation. This is about the change transfer cycle from NBD1 to NBD4. We can see the heat map of automatic change transfer for this material. We can see it about and next we have used the molecular dynamics simulation to simulate these materials. You can see the four materials. This is about the PS into this system. We can see it has been has been um, shows the solid state. So uh, by using this method, we can get the conclusion about this about the principle. This the concentration of PS in curve during the film fabrication can significantly influence the optical transparency mechanics robust and the energy storage performance of the resulting NDD films. Accordingly, we systematically evaluate the effect of various PS concentration. We found this according to previous studies, we evaluate four different concentration images of films premiered with very PPS ratios. All films display smooth, low positive surface without visible impurity, and their optical visibility greater raise and at a concentration of one point 75. The solution becomes overly viscous, leading to uneven film surface, which might attributed to enhanced performance chain intelligence. This results in improved mechanical robust and ductility. Definite both film stability and handling during sequence. However, excess PS ratio can reduce the relative concentration of NDD molecules, potentially calculating in the film is film's energy density. In conclusion, probability PS concentration can enhance the weak intermolecules interaction, reduce energy dissipation, and stabilize the stable the QC configure, thereby improving the energy storage performance. However, an overly high concentration PS would increase the viscosity of the system, decrease the diffusion capture of NDD molecule. We can see it from the figure H. Excess so we have to think about how to balance the PS ratio and this diffusion ability. And lastly, we have done system integration. This is about we can see figure E is a symmetrical diagram showing the integration of NBD film with PV cells and TEG. This is about we have used the MOST systems to PV cells and P and TEG. We can see the B and figure B and C is experimental results for the integration of the NBD film and PV cells. It's about we can we can integrate two systems to analyze the MOST system energy. Uh, this is about the conclusion. In the solution state NBD, we can the NBD for NBD2 expect a maximum. We can see it's enhance of 192, and NBD3 is the 17 upon converting the solution into the solid-state films with the thermal storage capacity of NBD4 was the highest, increased to 207, and demonstrated a significant efficiency of its solution state of performance. There is about the two point is about the molecule simulation. The 然后the third is about in PV integration. The NDD fields lower the PV cells temperature nearly 5 through UV observation, and converted high energy photons into storage chemical energy, enhances the overall system efficiency about 3%. In TEG cover, energy relies from the film mitigate the head-end energy drop, enhancing thermal electrical conversion efficiency. Moreover, the fully solid-state films eliminate the leakage concerns of liquid-based system and were completed with the excited PV modules. This study advanced of the NDD molecules in PT energy storage and analysis theoretical and experimental foundations of develop more efficient and stable MOST. So in the future, the molecular spectacle will twins might further enhance the latter electrical head conversion, providing innovation pathway for full spectacle solid energy utilize. So thank you for your listening. That's all.